Imagine you're in the cockpit, not as a passenger this time, as the pilot. You've leveled off at your normal cruising altitude, everything is calm, and then, hypothetically, the aircraft keeps climbing. Not because anything is wrong, just imagine, for a moment, that it keeps going. 41,000 feet, 43,000, 45,000, and beyond. What actually happens to the aircraft, physically, second by second, as it pushes past the altitude it was built for? Which system fails first? How much warning would you actually get? And is it something you could recover from, or is it already too late the moment it starts? In the last video, we broke down exactly why commercial jets stop climbing where they do. This time, we're going the other direction, walking through, step by step, what really happens if a plane pushes past that invisible line, using real numbers, real physiology, and real aviation history to show exactly how it plays out. There are 5 distinct failure points waiting up there, and they don't arrive one at a time politely. They stack on top of each other in a matter of minutes, sometimes seconds. And 2 of them have already happened to real aircraft, with real people on board, which is exactly why we know as much as we do about what this actually looks like. Let's start with the actual numbers, because 40,000 feet isn't some universal ceiling, it's roughly the middle of a range. Most narrow-body jets, like the Boeing 737 family, are certified up to around 41,000 feet. Larger wide-body aircraft tend to go a bit higher. The Boeing 787 and 777 families max out around 43,100 feet, and the Boeing 747-400 holds one of the highest certified ceilings in commercial service, close to 45,000 feet. These numbers are called the service ceiling, and they're not guesses. They're the product of exhaustive testing, calculated down to the specific combination of aircraft weight, temperature, and speed that keeps every one of the systems we're about to talk about operating with a safe margin. Cross meaningfully above that number, and you're not just breaking a rule on a checklist. You're leaving the zone where multiple separate safety margins were ever guaranteed to hold at the same time. You'll also hear pilots and air traffic controllers refer to altitude in flight levels rather than feet. Flight level 350 means 35,000 feet. Flight level 410 means 41,000 feet, and so on. It sounds like a small detail, but it matters here because every performance chart, every buffet margin diagram, and every certified limit in an aircraft's manual is built around specific flight levels, tested individually at specific weights and temperatures. There isn't a single blanket number where danger begins. There's a sliding scale where the safety margin at flight level 350 might be generous. The margin at flight level 410 is deliberately tight, and anything meaningfully above that is simply outside the range anyone ever tested it to hold. So let's actually do it. Let's say, hypothetically, an aircraft keeps climbing past its certified ceiling. Here's what starts happening, roughly in order. First, the engines quietly lose their margin. We already know jet engines need dense air to generate thrust efficiently, and that density keeps dropping as the aircraft climbs. Near the certified ceiling, the engines are already working close to the edge of their comfortable performance envelope. Push a few thousand feet beyond that, and the available thrust keeps shrinking, while the amount of thrust actually needed to sustain lift at that thin altitude keeps rising. The 2 numbers are moving toward each other. At some point, the engines simply can't produce enough push to keep accelerating the climb, and the aircraft's rate of climb slows to nearly nothing, then stalls out entirely. Not an aerodynamic stall yet, just an engine that's run out of room to give more. Pilots and flight engineers actually track this directly, through a number called rate of climb, measured in feet per minute. Near the bottom of a flight, a jet might comfortably climb at 2,000 or 3,000 feet per minute. As it approaches its certified ceiling, that number naturally tapers down toward a few hundred feet per minute, simply because there's less excess thrust available beyond what's needed just to maintain level flight. Push past the certified ceiling and keep demanding more altitude, and that number can approach zero, then go negative, meaning the aircraft, despite full or near full throttle, is no longer capable of climbing at all and may even start sinking back down on its own, regardless of what the controls are asking it to do. This is often the very first sign that a climb has gone too far. The airplane simply refuses to climb any higher, no matter how much throttle is applied, and starts quietly losing the very altitude it fought to gain. Second, the Coffin corner, which was already narrow, starts closing completely. Remember that shrinking gap between stall speed and maximum safe speed we talked about last time? At the certified ceiling, that gap might already be reduced to something like 20 or 30 knots on a typical airliner. Keep climbing past it, and that margin keeps collapsing, sometimes down to single digits. At this point, flying the aircraft in level flight becomes almost impossible to do smoothly. A slight gust, a small bank angle to correct course, or even normal air traffic control instructions to adjust heading can be enough to nudge the airspeed past one boundary or the other. Autopilot systems, which are built to fly within a comfortable envelope, can start struggling to hold a stable altitude and speed at the same time, sometimes triggering warnings or disconnecting entirely and handing control back to the crew in exactly the moment when the margin for human error has nearly disappeared. And hand-flying an aircraft manually in that narrow band is genuinely difficult, even for an experienced crew, because the usual visual and physical cues pilots rely on at lower altitudes, a clear sense of how much runway a correction buys you before things get uncomfortable, largely disappear. A control input that would be barely noticeable at 20,000 feet can be the difference between a stall buffet and a Mach buffet at the edge of the Coffin corner, which is exactly why airlines train crews to treat that zone as something to stay well clear of, not something to manage through skill alone. Third, the airframe starts to shake. If the aircraft drifts toward the high-speed side of that shrinking window, airflow over parts of the wing and fuselage begins approaching the speed of sound locally, even though the aircraft as a whole is still flying well below Mach 1. This creates small shockwaves on the wing surface, disrupting smooth airflow and causing a distinct, rapid vibration through the airframe known as Mach buffet. It's not subtle. Pilots describe it as a shuddering that builds in intensity, an unmistakable physical warning that the aircraft is pushing beyond its stable envelope. If the aircraft instead drifts toward the low-speed side, a different vibration appears, the stall buffet, warning that the wings are approaching the angle at which they'll stop producing reliable lift. Both warnings exist for the same reason, to give the crew a physical, unmistakable signal before the aircraft crosses from uncomfortable into uncontrollable. In the Coffin corner, though, both of those margins have shrunk so much that a correction to escape one buffet can push the aircraft straight into the other. Fourth, the fuselage itself comes under mounting stress. While all of this is happening aerodynamically, the fuselage is quietly fighting its own battle. As external air pressure keeps dropping with altitude, the pressure differential between the cabin, held at a comfortable equivalent of roughly 6,000 to 8,000 feet, and the outside atmosphere keeps growing. Every commercial aircraft is engineered and certified to hold a maximum differential pressure, tested through tens of thousands of simulated pressurization cycles before it's ever allowed to fly. That certification is tied directly to the altitude range the aircraft is meant to operate in. Push meaningfully beyond the certified ceiling, and the fuselage is being asked to contain a pressure difference it was never specifically tested to handle on a repeated basis. This is precisely the lesson the industry learned the hard way in the 1950s, when the de Havilland Comet, the world's first commercial jet, suffered a series of catastrophic in-flight structural failures traced back to metal fatigue from repeated pressurization cycles beyond what its fuselage could safely sustain. That investigation is the reason every jet built since uses reinforced, rounded fuselage openings and undergoes exhaustive fatigue testing. But the underlying principle hasn't changed. Every pressure vessel has a limit, and altitude is the variable that decides how hard that limit gets pushed. Fifth, the temperature outside becomes a problem of its own. At normal cruise altitudes, outside air temperature already sits somewhere around -55 to -60 degrees Celsius. Push higher, and while the temperature doesn't necessarily keep dropping in a straight line, the aircraft is now spending extended time in an environment its fuel system, hydraulics and structural materials weren't specifically certified to handle for prolonged periods at that combination of altitude and speed. Jet fuel can begin to gel or wax at extremely low temperatures if it's held there too long, which is exactly why fuel tanks are monitored for temperature throughout a flight, and why aircraft are certified with a minimum fuel temperature limit built into the flight manual. Hydraulic fluid, seals, and even the metal airframe itself behave differently at the edge of their tested temperature range than they do comfortably within it. None of this is a dramatic, instant failure on its own, but it's one more system quietly losing margin at exactly the same time as the engines, the wings, and the fuselage, which is the entire point. Nothing on a climbing aircraft fails in isolation. Every system loses a little bit of its safety buffer together, all at once. Sixth, and most dangerous, what happens if something actually gives way? If the pressurization system were to fail at that altitude, whether from a structural crack, a door seal problem, or a window failure, the cabin would lose pressure rapidly and the air available to breathe would drop to something close to what's actually outside the aircraft. This is where human physiology becomes the story, and the numbers here are worth understanding clearly. Aviation medicine uses a measurement called time of useful consciousness, which is exactly what it sounds like. How long a person can still think clearly and act correctly after their oxygen supply drops. At around 25,000 feet, that window is roughly 3 to 5 minutes. At 35,000 feet, it shrinks dramatically to somewhere between 30 and 60 seconds. Push into the low 40,000s, and that window can fall to as little as 15 to 20 seconds, barely enough time to recognize what's happening and reach for an oxygen mask before judgment itself starts to fail. A sudden decompression at that altitude isn't quiet either. The pressure difference releasing all at once typically produces a loud bang or rushing roar, a visible fog inside the cabin as the moisture in the air instantly condenses from the rapid drop in temperature and pressure, and a noticeable chill as outside air, sitting far below freezing, floods into what had been a comfortable cabin. Loose items can be pulled toward any opening. None of it is subtle, which is intentional. The more obvious the event, the faster a trained crew can recognize exactly what's happening and respond. This is exactly why oxygen masks are designed to drop automatically and immediately in a decompression event, and why pilots are trained to put on their own mask the instant a warning appears, before doing anything else, and to begin an emergency descent to a breathable altitude as quickly as the aircraft can safely manage it, typically diving toward 10,000 feet, where the air is thick enough to breathe normally, without supplemental oxygen at all. This isn't a hypothetical danger dreamed up for a video. On October 25, 1999, a Learjet carrying professional golfer Payne Stewart and 5 others climbed to its cleared cruising altitude and then stopped responding to air traffic control entirely. Fighter jets scrambled to intercept the aircraft, found it still flying straight and level on autopilot, engines running normally, but with the cockpit windows fogged over from the inside and no visible movement from anyone on board. Investigators later concluded that the aircraft had lost cabin pressure and that everyone aboard had been incapacitated by lack of oxygen before they were able to respond. The Learjet continued flying on autopilot for close to 4 hours, watched by military aircraft the entire way, until it eventually ran out of fuel. It's a sobering reminder of exactly why the numbers around time of useful consciousness aren't just textbook figures. At high altitude, the difference between a controlled response and total incapacitation can be a matter of seconds, not minutes. A second, better documented case shows how insidious a slow pressurization failure can be, as opposed to a sudden one. In August 2005, a Boeing 737, operated by Helios Airways, took off with its pressurization system left in manual mode after maintenance, rather than the automatic setting it should have been on. As the aircraft climbed, the cabin altitude rose right along with it, instead of staying comfortably low. A warning horn did sound in the cockpit, but investigators found it used the same tone as an unrelated takeoff configuration warning, and the crew appears to have misidentified it in the moment. By the time the aircraft reached its cruising altitude, the crew had already become impaired by hypoxia without ever consciously registering what was happening to them, and the aircraft continued flying on autopilot for roughly 2 more hours before running out of fuel. It remains one of the clearest real-world demonstrations of how gradual, rather than explosive, a pressurization failure can be, and how completely hypoxia can undermine a person's ability to recognize their own impairment in real time. In direct response to this accident, regulators required aircraft manufacturers to give cabin altitude warnings a distinct, unmistakable sound, separate from every other cockpit alert, specifically so a crew could never again confuse it for something else. So, given all of that, here's the important part. Why doesn't this happen on your flight? Because commercial airliners are deliberately, aggressively engineered to stay far away from every single one of these thresholds. Airlines cruise thousands of feet below the certified service ceiling, specifically to keep a comfortable buffer in the coffin corner. Autopilot and flight management systems are programmed with hard altitude and speed protections that prevent a gradual climb from ever wandering into dangerous territory unnoticed. Fuselages are pressure tested to cycle counts many times higher than an aircraft will ever experience across its entire operational lifetime. Pilots train specifically for rapid decompression scenarios in simulators and altitude chambers, practicing the exact mask-first response that turns a 15-second window into a survivable situation instead of a fatal one. And modern jets carry multiple redundant pressurization systems so that a single component failure doesn't automatically mean a total loss of cabin pressure. Cabin altitude warning horns today use a dedicated, unmistakable tone precisely because of what happened on that Helios flight, and pre-flight checklists now include specific, redundant verification that the pressurization mode is correctly set before the aircraft ever leaves the gate. Every fuselage carries pressure relief valves engineered to prevent the cabin-to-outside differential from ever exceeding its certified limit in the first place, venting excess pressure automatically rather than letting stress build toward a structural failure. Passenger oxygen systems are sized to supply breathable air for the entire time it takes to complete an emergency descent, and pilots carry their own separate, faster-acting oxygen supply, specifically because they're the ones who need to remain sharp enough to fly the aircraft down. Every one of the 5 failure points we just walked through has a dedicated engineering safeguard, a checklist item, or a piece of certification testing built specifically around preventing it from ever being tested for real at 40,000 feet with passengers on board. It's also worth remembering that some aircraft are built specifically to operate in this extreme zone on purpose, with completely different engineering to match. The Concorde cruised at roughly 60,000 feet for decades without incident, because every system on board, from the engines to the fuselage to the flight envelope protections, was designed around operating there. The Lockheed U-2 has flown reconnaissance missions above 70,000 feet since the 1950s, deliberately living inside a coffin corner so narrow that its margin between stall and Mach buffet can be as tight as 5 knots, flown by pilots trained for years to handle exactly that. The difference between those aircraft and the plane you fly on vacation isn't luck, it's design intent, from the very first blueprint. So if you ever find yourself wondering, mid-flight, whether the aircraft could simply climb a little higher to smooth out some turbulence or shave a few minutes off the trip, now you know exactly why it doesn't. It's not caution for caution's sake. It's the result of a very precise, very deliberate buffer between where the aircraft cruises and where 4 or 5 separate physical systems would start running out of margin at almost exactly the same time. The pilots flying you aren't avoiding that altitude because they're uncertain about the aircraft's capabilities. They're avoiding it because they understand those capabilities better than anyone, and they know exactly where the edge of the safe envelope actually is. That's really the through line across both of these videos. The sky isn't an open, unlimited space that airplanes simply choose not to explore. It's a carefully mapped, rigorously tested corridor, and every number stamped in a flight manual exists because someone, somewhere, tested exactly what happens past it, sometimes in a lab, sometimes tragically, for real. 5 separate systems, each with its own hidden limit, all converging on the same narrow band of sky, and every single one of them backed by a specific engineering fix born from decades of hard-earned lessons. So the next time your flight climbs to its cruising altitude and levels off, know that the number on the display isn't a suggestion, and it isn't the aircraft playing it safe out of caution alone. It's the precise, tested edge of where every one of those systems is guaranteed to keep working together. If this one helped the picture click into place, drop a like and subscribe for more of these deep dives into how aviation actually works. See you in the next one.